Hey guys, in this video we will do graph classification problem. The dataset that we use in this video will be the gene dataset. So in this dataset we have 1113 graphs which are partitioned into two classes, and each graph range between 10 to 500 nodes. We will do two graph neural networks to classify this graph dataset. The first graph neural networks we will use GCN as the convolution layer. In the second one, we will use SAGEConv as the convolution layer of the graph. So in each case, we have an input. We process the input by putting it through an atom encoder to encode all the nodes into a common feature dimensions. The reason is because in the original graph, all the nodes have different feature dimensions, so we need to encode them into a common feature dimension before we proceed further into graph convolution layers. And in the final layer, we take the mean of all the nodes for doing classification. And now I'm going to go through the code. So the dataset that we use, this should be a code block. I need to import the GL first. As you can see, in this case, there are two classes. The feature dimension is 3. Sorry, just now I mentioned that the nodes do not have the common feature dimension. In fact, they have common feature dimension, but it is often a standard practice to map this feature dimension into a higher dimension before continue processing them through the convolution layer. We have 1113 graph, and here I extract the first graph. The first graph has 42 nodes, 200 each, and other information about the label. The label for the first graph is 0. Well, it should be noted that here we have a highly imbalanced data set in which there are a lot of zeros and very few ones. So the classification for such highly unbalanced data set is much more difficult than a balanced data set. First, we are going to prepare the train and the test set. I need to import NumPy. So we will create data loader from bgl dot data loading import graph data loader. Let me make this bigger. From touch.util.data.sampler import a random sampler. Well, we want to keep 20% for training, so 80% for training and 20% for testing. So we will randomly permute the chain indices between so here 0 and train using the random sampler. And then we will randomly permute the test indices, train indices, randomly permute test indices. So we obtain a test sampler for range here should be from numTrain to length dataset. So now train loader is graph data loader, passing in the dataset, sampler, the chain sampler. We will have batch size equal to 4. Drop last is false. And in the same way, we will create a test loader. So here we need the test sampler. Well, let's print out a batch in the chain loader to see what is going on. So here, well, when we do this, all the 4 graphs in a single batch, they are stitched together into one big graph, and I will call this one big graph the batch graph. Let's it a chain loader. So the purpose of stitching all the 4 graphs into one big graph is to facilitate the computation. So we will print the batch graph, and we also print the labels. Yeah, so here in this batch graph, which is the 4 graphs together, we have 167 nodes, 755 each, and the labels are 0, 1, 0, 0. Well, in the next block of code, I want to illustrate that the dataset that we are working on is a highly imbalanced dataset. So I will first do a random prediction on the testset, and whatever we obtain later, we'll compare it with the random predictions. So first, let's check the labels of the data. We want to focus on the test label. So yeah, so here the test label is from the num chain to the end. So random probability random will be the number of ones that we have divided by the length of the labels. Because let's say here in this collection of labels, if it is a balanced data where we have 50% 1 and 50% zeros, and by a random prediction, then we can correctly predict with 50%. However, for the case where the data is imbalanced, where there are only 10% is 1 and 90% is 0, then the probability for correctly predicting 1 will be 1/10. So now I can print out random prediction random. So the probability for a random prediction will be 0.2, that is about 20%. So next, whatever we do, we will try to compare with this number. So in the second part, we will create a model which consists of GCN graph convolution as our convolution layer. So here I will need to import a few things. tgl.nn import graph convolutions, and I want to import the built-in NodeEncoder ogb.graph predictions.NodeEncoder import item encoder. Let me make sure I don't make a typo here. That looks fine. So this is the the encoder that are used for items usually used for items in molecular graph. Okay, so here is our model. Our model consists of item encoder, and we feed it through a sequence of GCN with batch normalization and relu activations, and on top we take the mean of all the nodes. GNN GCN and n.module. For the init method, we want to have in dimension, hidden dimension, out dimensions. Hidden layers here mean the number of blocks of graph convolutions. Let's set it to 8. Well, first we will have a node encoder on the input. This could be the item encoder where we encode all the node into hidden dimensions. Self dot h layer is equal to h layer. And next we want to initiate a stack of GCN. Self dot convos here is nn dot module list graph convolutions hidden dim to hidden dim over well, hidden dim h layers -1. The last one we want to have the output out dimensions, so we append graph convolution where we map to the out dimension. This is the last layers. And that is the stack of GCN. Well, here we have blocks of GCN and batch norm and relus. So here we also want to have a stack of batch normalizations. So we have nn dot module list. So here we use touch batch normalization from touch.nn. For in range h layers -1. So for the last layer we don't need to normalize, and now we will do the forward pass. So G is our input graph and X is the input node features. So first we will do a node encoding h equal to self.node encoder x. We pass h through the sequence of convolution and batch norm and relu. Y in range self.h layer -1 h self.convolution I. So this need to pass G and H, and we will do relu on the batch normalizations. So these are the middle layers, and the last convolution layers. GH. Now for the output, we will compute the mean of all the node features. Mean of all node features. So first we will assign the node features to the keyword h, and the output put here is I call out logits mean, it just mean for the nodes, mean features. We can use the begin function from DGL mean nodes. We take the mean on all the features h. This should have dimension out dim. If you want to get probabilities, then you can apply a softmax, but where you just use the logit, so we return the mean features. So that's it for our model. Here we have run into the error of having no OGB because we haven't installed it. So I should have installed it in the beginning here. Alright, so now let's run everything again. Okay, it works now. Let's do a test for our model. So in dimension will be the dimension from our dataset. Hidden dimension, let's choose 64. Our dimension should be the number of classes we have. So model GN and GCN, take in dimensions, hidden dimensions, our dimension as parameters. Let's see how many parameters that we have for this model. And we want to check maybe one forward pass to see if there is any error. So touch.no grad, we don't want to keep track of the gradient. Red logits. Remember that we created one batch graph before, so we can just use it. And we also need to pass in the data. The data name is attribute. For the data type, we need to convert it to long. So let's print out the prediction logits. Alright, so here our model has 0.04 million parameters, and here are the prediction logits. So it looks good. Now it remains to train this model. Let's set a manual seed for reproducible result. Let's call the model here again. The optimizer that we use will be ADMW. With learning rate equal to 4e minus 3. Let's just try it out first. This is the learning rate I often use for ADMW. Number of epochs is 100. For epoch, in range number of epochs, the total loss is 0. Now we are going to loop through the train loader, compute the logits, batch graph dot and data. loss will be cross entropy between the logits and the labels. Need to zero grad the optimizer, do load backward, and optimizer.step. Here is the batch loss. We want to update the total loss by adding it with the batch loss. Well, our total loss need to divide by the number of batches, so loss total should be divided by the number of batches. If epoch, we want to print out for every 5 epoch. When the epoch is the final epoch, we want to print out the loss. All right, so here it is. Well, we have a pretty big data set, so if we go back here, our data has over 1000 graphs. So this will take some time to run, as you can see. While it is running, I'm going to do the identical things, but in this part I will be using the graph convolution as the convolution layer in the graph. Our model is the same, the only difference is that we use SAGEConv instead of GCN. So here let's do it below while it is running above. So here first I need to import 6conv. It is a Python block. Why it doesn't suggest me SAGEConv? No, this should be capital letter. Because everything else stays the same, so I will be copying what I have written here. And the only change that I would need to make is in the convolution layer, where I need to pass in SAGEConv. And in SAGEConv, I need to specify the aggregator type. It is min. Well, the rest will be identical. So, yeah. And we will also train this one using identical. So here, let's copy and paste it down. Let me see, I need to change the model. Well, it should be GNN SAGE. And I guess that's it. So right now it's still running. Perhaps it is a good idea now to write the evaluations. So we want to evaluate on the test set. If do you have recall in the beginning we have written now that on the test set random prediction give 20% correct probabilities. So we want to compare it with this number. Well, So now let's evaluate on the dataset. So number of correct predictions, number of data, and the loss on the dataset. We initiate with 0 with touch.no-class. So here you can do all these in test functions also. For batch graph labels in test loader, we want to obtain the logits. Batch graph, batch graph dot and data. The keyword to extract node features is attribute. Loss will be cross entropy between the logits and the labels. Total loss. Now for the number of correct, note that the logits here, to get the predictions on the logits, we simply take the argmax of the logits. So predictions will be logits.argmax on the second dimensions, and we want to compare this with the labels. Take the sum to see how many of them are the same. Now number of data will be updated with the number of labels. Alright, so now we can print out let's say GNN, GCN, test loss. So here, well, I shouldn't do loss total here, but loss total should be divided by the length of the loader, the number of batches. Loss total, let's print it out to 4 decimal places, and test accuracy will be let's have test accuracy here will be the number of correct prediction divided by the number of data. So test accuracy up to 4 decimal places. Alright, so the training here has done. Looking through the loss, we can see it goes down, but not by much. Right? Our model is too simple to handle this data, in fact, and the purpose for this this video is not to train this data to the best, in which we will need a much more complicated model, but to do graph classification. I hope the result is not too bad. Okay, bad news is that it looks not good at all, where the accuracy is only 23%. That is slightly better than the random prediction. The random prediction is 20%. So now let's hope that with SAGEConv things will be better. So here let's initiate the model. Well, let's set a different random seed with the hope that it is better, but I guess it will be probably the same. So we start with the loss 0.65. Well, it feels like worse because here we start with the loss from 0.59. This will take a while to run. Okay, so in the meantime, let's copy this block of code, put it out here. I will pause the video here and come back when the training is finished. Here we have completed the training, and after 100 epochs we are able to get to the loss 0.5. Well, if we compare this to the starting loss, it's not much. The reason is that this model is too simple to handle this type of data. However, if you compare to the previous model where we use GCN, the loss is 0.51, so it's a little better, and we hope the evaluation on the dataset is better. Well, this time the test accuracy is 33% as compared to 23% from GCN, and a random probability will be 20%. So that is an improvement, even though it's still very small. And that's it for this video. I hope you enjoy it. See you next time.